So in our understanding of gas laws, we first have to look at matter. Matter is anything that has mass and takes up space. Matter comes to us in three basic forms: solids, liquids, and gases. There are similarities and differences to all three states of matter. The similarities are that they're all a collection of very small particles. We call those little particles atoms or molecules. You can kind of think of those little particles as little tiny marbles. Okay? So in solids, those particles are very close together and exert very attractive forces on each other. They have definite volume and shape. They can't flow. They retain their shape, and they cannot be compressed. With liquids, the particles are closer together and they exert attractive forces on each other. They have a definite volume but an indefinite shape. Liquids can flow, but those molecules stay together. And they, again, cannot be compressed. Gases are a little bit different. In gases, the particles move rapidly, independent of each other, and they don't attract one another. Okay, so they're not bound to one another. Each particle independently moves. They have an indefinite shape and an indefinite volume. So gases can take the shape of their container. So that's why if you spray a smelling spray in a room, it will diffuse throughout the room and fill up the entire room. They can be compressed and they can easily change their volume. So here is a little picture. Here's gases. They're zipping all around. There's total disorder. There's a lot of empty space. Particles have complete freedom of motion. In a liquid, there's disorder. The particles are clusters of particles are free to move relative to each other. And the particles are relatively close together. And with a solid, it's an ordered arrangement. And the particles are basically fixed in their position. It's because of the differences in the way that the particles of gases are compared to liquids and solids that result in the behaviors and the properties of gases. Gases are able to diffuse throughout a room or effuse through an opening. Now, we can explain the behavior of gases, the kinetic molecular theory. So kinetic molecular theory explains the behavior of gases. And there's four parts to kinetic molecular theory. First, gases consist of tiny particles separated by relatively large distances. Second, gas molecules are in constant motion. They travel in straight lines between collisions. They collide with each other. They collide with the walls of whatever container they're in. And in between those collisions, they travel in straight lines. Third, at any given Kelvin temperature, the average kinetic energy of all the molecules of a gas is directly proportional to that temperature. What that means is their energy of motion, that's kinetic energy, is the energy of motion, is directly related, directly proportional to the temperature. So as the temperature increases, it's going to increase because there is an increase in kinetic energy. The particles are moving faster. The fourth part of kinetic molecular theory is that at the same temperature, all gases will have the same average kinetic energy in their molecules. So regardless of which type of gas we're talking about, there is going to be the same kinetic energy in the molecules of that gas at equal temperatures. So now the behavior of the gases in our atmosphere results in what we call atmospheric pressure. Now, we define pressure as the force over area, right? So forces can be measured in what are called newtons, or they can be measured in pounds, right? Areas, square inches, square meters, that sort of thing. So with pressure, we end up then with units of pressure. Usually we see PSI, which stands for pounds per square inch. Other units of pressure include the atmosphere, or the torr, or what we call millimeters of mercury. And really, all of this atmospheric pressure is a result of the small particles of gases in our atmosphere, and gravity pulls them down, and so we end up with greater pressure at the surface of the Earth than we do farther away. So really, you can think of us as living under a sea of air molecules. Now, this kinetic molecular theory can be modeled by the gas laws. And there are three primary gas laws, right? There's what's called Boyle's law, Charles' law, and Guy-Lusac's law. And when it comes to gases, then there are three main variables that we deal with. There are pressure, there's volume, and there's temperature. And we denote those as P for pressure, V for volume, or a T for temperature. For each of these three gas laws, then, at least one of those variables is held constant, which means it doesn't change at all. For example, with Boyle's law works only under conditions of constant temperature. Okay? And when we're talking about temperature with all of these gas laws, the temperature that we're talking about has to be in Kelvin. Okay, so if we see situations where the temperature is given to us in degrees Celsius, we have to convert those degrees Celsius to Kelvin. And the way you do that is with any Kelvin temperature. To find the Kelvin temperature, you take the degrees Celsius, you add 273. And you do the opposite to find the degrees Celsius. You can take the Kelvin temperature minus 273, and that will give you the Celsius temperature. But anyway, back to Boyle's law. Boyle's law tells us then that for any given amount of gas held at a constant temperature, the pressure and the volume are inversely proportional, which means as the pressure is increased, the volume will have to decrease. If the volume is increased, our pressure will decrease. Now, for Charles' law, we're talking about a situation under constant pressure. Okay, so for Charles' law, our gases are held at a constant pressure. And what Charles' law will tell us then is that under constant pressure, the volume is directly related to the temperature. And then finally, under conditions of constant volume, we use Guy-Lussac's law, which tells us that the pressure is directly related to the temperature. As one increases, the other increases. As one decreases, the other decreases. So we use these gas laws under conditions of where we're able to really control one of those variables, under conditions of constant pressure or constant temperature or constant volume. In reality, we're not often able to keep those things constant. So what we have is what's called the combined gas law. So we're able to use the combined gas law in situations where more than one variable changes, right? So maybe we're having the volume change and the temperature change, or the pressure and the temperature are changing, or the pressure and the volume are changing. And that's in the conditions when more than one of these variables is changing, we're going to use the combined gas law. And finally, in chemistry, we often want to be able to talk about the amount of gas that is in a sample of gas. So we want to be able to talk about the number of moles of gas, okay? Remember, one mole is simply 6.022 times 10 to the 23 things. So a mole of gas just means that we have 6.022 times 10 to the 23 particles of gas. So this formula, the ideal gas law, works best for gases that are called ideal gases. So an ideal gas is defined as one in which all the collisions between the molecules or the atoms in that gas are perfectly elastic, which means that they completely bounce off of each other. There are no attractive forces between the particles within that gas. So you can kind of picture an ideal gas then as the number of perfectly hard spheres that collide but that otherwise don't interact with each other. All right. Many common gases exhibit behavior very close to that of an ideal gas at high temperatures and low pressure. So this ideal gas law works for those idealized cases where our gas behaves perfectly according to the kinetic molecular theory. In reality, gases don't behave that way unless they're under high temperature or low pressure. So, in working then with the ideal gas law, let's look at some of the variables that are involved here. So first, we've got the same pressure, we've got same volume, we've got same temperature, which of course is in the Kelvin temperature. This N right here means number of moles. And this R right here is what is called the gas law constant, or the gas constant. There are three gas constants that we would use depending upon the pressure units in the problem we're dealing with. If in the problem that we're dealing with, the pressure is given in atmospheres, we would use 0.082 as R. For a problem where we're given pressure in kilopascals or kPa, we would use 8.314 as our R. And for a problem dealing with millimeters of mercury, we'd use 62.4 as our gas constant for R. So our ideal gas law can be used to make predictions about the pressure, temperature, volume, and as well as the number of particles of a gas. So if we know any of those four variables, we can rearrange this equation to solve for the unknown. So that's your summary of gas laws. You're welcome to watch the video as many times as you need to. Rewind, pause it, go back, and have fun studying.